Okay, well, hello everyone. Thank you, Abdullah, for arranging this. I think it's a very good venue just to educate engineers that are working in the industry. My history really is with gas analysis systems and dew point measurements. So that's water dew point and hydrocarbon dew point. What we're doing now these days is it's come out of a request from a midstream company, a gas transmission company, if you like, that said we know that liquids are getting into the gas without tripping any alarms, and challenged us basically to develop a piece of kit that would detect this liquid carryover. They'd just written off a gas turbine power station, and when they examined the liquids, they understood that actually it was nothing to do with them. It was actually glycol, which is used by their suppliers. So somehow glycol is getting all the way through their custody transfer point, through the pipeline, 100 miles down the pipeline to a gas-fired power station. We've developed a system to do that now. It's taken us, 3 years to find out how not to do it, and then a few more years to get the certification and the patents and everything else that needs to go alongside that. So what we're now learning is quite interesting. It's redefining what we understand to be in the pipeline. We're finding far more liquids in the pipeline than the gas analysis would suggest. And I've got a few videos here. So what we're going to do, just an introduction to liquid carryover, go through hydrocarbon dew point and the gas journey, videos of liquid carryover events, just to show you some examples of what we're seeing in the field, really, and how we're using machine learning to improve separator performance, really. If we've got time, we've got a case study in the USA and some key takeaways. So
Yes,
really,
you have a full hour. It's guaranteed. It's all my bet for any time lingering that
okay.
happened. Yeah.
Thanks, Abdullah. This is the gas journey from the gas wells. This tube map, if you like, is a very, very simplified version of the gas processing system. So it comes from the gas well into gas processing. I've shown 3 trains here, and then into the transmission line to deliver the gas to maybe an LNG plant, a power station, or maybe domestic supply. So what we're looking at when we look at this gas journey is where are these liquids coming from? And at every stage along here where we see an arrow is the possibility of liquids coming into contact with the gas. So from the gas well, as we've just heard, there's liquids being injected, bactericide, hydrate inhibitor, corrosion inhibitor as well, on top of the water, the sand, the crude oil, and maybe condensate that's coming up with that gas as well. So sometimes there's a compressor here between the gas well and the gas processing plant. Certainly, if that's a remote station, then there's a phase separator in front of the compressor to protect the compressor. And then sometimes that liquid might just be re-injected and then taken out again when it gets to the plant here. So when we go to the plant here, then the important thing is this is where the liquids are being taken out. Hopefully one should equal the other. We're finding that's not always the case. So the important thing really is the front end of gas processing. So in the ideal world, only gas moves forward into gas processing. But if there's hydrocarbon liquids and maybe some other the liquids contain surfactants, then we can see foaming and fouling caused in the amine system here, the sulfur removal system. And then sometimes there are the amine in this system then gets carried over into the glycol system, the dehydrator, and contaminates the glycol to quite a large degree sometimes. And then there's another phase separator here to separate out the liquid and the gas. And then that's carried forward to the NGL, the NGL recovery system. So in the NGL recovery system, now the gas it's sweet. The sulfur has been removed. It's now dry. Now the temperature can be taken down, usually to -20 or -30 degrees C, to intentionally drop out as much of those NGLs as possible. They're quite key liquids that have a high value. So it's in the interest of the gas processor to drop out as many of those liquids as we can. And there's a phase separator there to make sure that those liquids are actually dropped out. So the important thing to note, particularly in this section here, is two things need to happen. That temperature needs to be achieved, and usually that's achieved by Joule-Thomson, expanding the gas, which causes a rapid cooling. And then phase separation. Whilst the gas is at that low temperature, those liquids need to be removed. That's important. I'll go into that a little bit more later. A lot of the systems here that we put in are at the custody transfer point. So at this point, the gas is handed over either to a separate company, or sometimes it's the same company, but it's certainly a different section, different department. And at the custody transfer point, it's important that that gas is dry for many reasons we'll go into. But normally the agreement is that there is dry gas at this point. And that's important because of just down here, there's normally a compressor that takes the gas up to about 70 bar, 1,000 psi. For transmission into the gas line. So if you want the gas to move quickly, you need a high pressure at the start and a low pressure at the end, so that it encourages the gas to move down that pipeline as quickly as possible. So every 100 miles or so, there's another compressor station to boost that pressure and to move that gas on its way. So the important things, or the hazardous areas, really are, in particular, the compressor stations. They are liable to liquid carryover. But these are the hazardous areas here, where this phase separation in front of this compressor, this phase separation here at the front end, if we can really get a handle on liquid carryover here, then we can reduce plant failures, the foaming and the fouling that occur in amine systems, and reduce downtime and shut-ins, really. And then we go further down the line. We've done a few underground storage facilities where the gas is taken off the transmission line, stored underground again, but of course that then means it's soaking wet. So there is another dehydration system here, usually a glycol-based system. So a lot of glycol comes into contact with the gas and should then be taken out. And we're finding that generally these sites are a source of quite high levels of contamination. Other networks as well, depending on the size of the network, it might be connected to other networks, and obviously that's another source as well. But whether you're the supplier or the receiver, then liquid carryover generally is bad news. From a gas processing plant, the supplier's point of view, or the receiver, the gas network, then there's going to be problems here. We see fouling at the top of a gas plant here, amine plant, and this is fouling of a heat exchanger, usually due to defoamer. If there's foaming going on, then normally the normal recovery from that is to add defoamer, and that quite often causes further problems with contamination inside heat exchangers and causing all sorts of further problems down the line. So this is why we're saying, if we can stop this liquid coming in the first place, at least get a handle on what it is and improve that situation, it pays dividends. Certainly in terms of lost production, low efficiency, and loss of amine and glycol, the biggest one we're finding is NGLs are given away for free. So these natural gas liquids, are actually entrained in the gas at the export on the export line. and that means that they're getting into the gas line for free. They're not measured as part of the gas analysis. We'll go into that later. So the supplier, if you like, is losing revenue. And then on the receiver side, as a gas transmission system, a midstream company, if you like, moving the gas from A to B, there are a number of issues there. Increased pigging, certainly, and disposal costs are the biggest one there. If the gas is contaminated, then the pigging frequency needs to be increased. Errors in fiscal measurement. So if the gas has got liquids in, then the flow meters generally will overread. It doesn't really matter on the technique of the flow meter. It could be an orifice plate, ultrasonic, or maybe even Coriolis, but it's going to cause an error in the fiscal metering and flow assurance. Increased pressure drop across that transmission system, so the compressors at the far end are going to have to work a lot harder with wet gas than they are with dry gas. Reduced line capacity, and then increased compressor servicing costs. So we'll go into that as well. But these three pictures down here, this is results of pigging. This is actually fairly minor contamination. We've got a lot worse than pictures than that. This is a compressor that's gone up because of liquid carryover. This happens remarkably frequently. There's just been 2 incidents in the States that liquid carryover has caused the compressor to go up. And this final one here is the gas pipeline rupture at New Mexico, at Carlsbad, New Mexico, where liquid pooled at a low point in the pipeline and corroded the pipeline to point of rupture. This is the flame after that initial explosion. These are bridge supports here, and those tiny things on the horizon are trees. It's about a 300-foot flame there. So the gas pipeline was only running at about 40 bar when this went up. Still, it's quite a big bang. So asset integrity is really key when it comes to liquid carryover. But in terms of money, then it's millions of dollars, thousands of dollars every month, millions of dollars a year on both sides of the fence line lost every year due to liquid carryover. If you get a chance, there's this Trends in Tragedy was written by amine experts, and they studied 400 cases of amine plant failures. So each of those failures cost somewhere between $250,000 to $250 million, depending on the size of the plant and the size of the problem. But a bit of a spoiler, really, it came up with three main conclusions, two of which, corrosion and foaming, are directly attributed to liquid carryover. And then if we move across to the transportation or transmission lines, there's another study done by the Health and Safety Executive on 71 failures of dry gas seals on compressors. Now, as the name suggests, a dry gas seal requires dry gas. The gas pressure governs the space between the static part of a compressor and the rotating part of the compressor, and that space is only about 7 microns. And if that space is filled with liquid, it will convey temperature far more than a gas does. And then those two components go out of specification and touch, and that wear will accelerate at quite a high rate. So the design of a dry gas seal is about 5 years. That's from both manufacturers' requirements and users' requirements. But this study found that actually they're only lasting about a year. And in 100% of cases, there were liquid ingress between the faces of those seals. So our mission, quite simply, stop contamination in gas supplies. Really, we're seeing a lot of hidden liquids, so liquids that are present that operators didn't know that they're there before we put our piece of kit in. So separators and filters are not 100% efficient. Got some numbers on that in a minute, but they often operate below the operator's expectations. So the fact that a separator or a filter is in front of a compressor doesn't mean necessarily that, yeah, job done, that compressor's safe. then we still need to make sure that that is operating as best as it can to stop that liquid getting through. So don't assume the knockout pot, as say, just in front of the compressor will keep the downstream equipment safe, really. So hydrocarbon dew point is one of those key parameters, key metrics that everybody uses to ensure that the gas remains dry. And as I say, my history is with hydrocarbon dew point, and so it's quite a shock when we started going out into the real world to find that whilst hydrocarbon dew point has been reported as quite a low level, that you wouldn't expect to see condensation there, in many cases we do. And I'll show you some examples of that. So we're just questioning, have we discovered some fundamental flaw in how hydrocarbon dew point is reported and used? To give you an example, well, in addition to that, compressor oil and glycol are not actually monitored by any analyzer at all in the system. So if there is compressor oil or glycol in the system, there's no analyzer in the standard suite of analyzers at the custody transfer point that's going to pick it up. And that's how really those liquids are getting through these systems, because nobody knows they're there. Just to give you an idea on cost, liquid volume fraction, or LVF, is used quite often in mixed phase flows. It's merely an expression of how much of that flow is gas phase and how much is liquid phase. And usually we're talking about 0.1 of a US gallon per million cubic foot, or as a separator spec, or certainly below 0.1 LVF, liquid volume fraction. But you can see that translates even on, this is an example of a system with 100 million standard cubic feet per day, which is about the standard size of a gas plant in the US, at 1,000 PSI. So one thing I always like to do is visualize, well, what does this 100 million standard cubic foot look like? What, if we were to draw a cube of this gas. So if you imagine a soccer field, a football field on the ground, and you have another soccer field right next door to it, that basically is a square on the ground. I put a cube on that, and that approximately is 100 million standard cubic foot. And so these gas plants are producing that amount of gas at atmospheric pressure, that amount of gas every day. So what we're saying is, even with this gas flow here, then 0.1 LVF is still somewhere around $4 to $6 million a year of lost revenue. Certainly enough to take some action. So the other problem is for, if you like, the end users. So the end user might be an LNG plant, might be a power plant. Both of those have problems. In particular, LNG plants, they can cope with NGLs quite well, but somehow these heavy ends, the compressor oil, C12 plus, are getting through the filtration system. They're getting through the molecular sieve beds all the way into the cold box. And when that happens, you can see this is over a 30-day period, and this is the pressure difference across the cold box, which builds due to compressor oil. Basically, it gets down to about -50 and then locks up solid and starts blocking that heat exchanger. And the calculations done by ConocoPhillips and Dale Embry mean that it's only 3 ppb of that material that is enough to start that restriction in 30 days. So separator systems, and we take this in two stages really. I've got an example there of a vertical one and a horizontal one. So these systems are good for knocking out sort of the heavy end, if you like, the 30 to 50 micron mist particles. The idea is that the inlet gas here comes in at a certain velocity, it comes into the wider diameter of the vessel and slows down, drops its liquid loading, and the gas phase moves up to the top here. There are, though, I mean, this is probably a poor example of a baffle, but if there was nothing here, then this inlet gas would just go head straight for the outlet. That's where the lowest pressure is. So the flow would be straight from here to the outlet, and there'd be a lot of static gas in between. So it's not necessarily slowing down in the way it's intended. So there are, in these separator systems, a series of baffles to spread that gas flow out across the whole of the diameter, and same in the horizontal one where you can separate the oil and the water. But there are a number of things that can go wrong with there. Partial demister blockage. So these demister pads at the top here can get blocked by just rubbish and gunk and whatever. And so the remaining part of that demister pad has an increased velocity in the gas going through it. Swirl at the gas entry. If there's a bend just upstream of the entry point, then you're going to put some swirl on there, which means the gas sort of swirls round and may not do what you think it's going to do. The liquid level is set too high. If that is too high, then the gas will re-entrain that liquid and carry it on up to the demister pad. And partial blockage of the outlet here as well. So velocity decrease not fully achieved, as baffles do not allow gas to be distributed across the full diameter. So the design of these baffles is key in getting a really good separation of those large diameter microns. And then there was some work done by the Southwest Research Institute in the States, and you can see the remarkable difference here between using nitrogen and natural gas on the performance. So at 20 bar, the nitrogen and natural gas are about the same. At 50 bar, again, about the same here, but as the pressure increases, then there's a big difference between the two. The other thing, obviously, to notice is that as the velocity of the gas increases, obviously the efficiency of that separation process decreases. And that's why a lot of times when a separator is put in and then an extra well is added and another one, then that separation process isn't necessarily acting as it should do. In fact, during this STAR program, Southwest Research did 471 tests on 7 different vendors of separators, and only 14 tests, that's about 3% of those tests, actually met the 0.1 gallon per million cubic foot limit or specification, which is quite surprising, really. And you can see a lot of the results were considerably higher than that, somewhere between 10 and 100 gallons, really. So moving on from that separation, then we go into what's known as depth filters or polishing to remove the smaller microns. I've illustrated a horizontal filter bed where you have filter cartridges going in there. Quite often, a better design for a liquid separation is a vertical system, and the problem is that the lower half or the lower quarter of these cartridges get saturated and no longer work as a depth filter. So when we put one of our cameras downstream of these systems, we're looking at what is the filter letting through, and normally operators determine whether these filters need changing or not by looking at the differential pressure. So the differential pressure is telling them how much how much the filter has stopped, and downstream we're looking at how much the filter has let through. And then there's a number of different things, really, from an operational basis that can go wrong. There's been a few instances where actually, when they've examined the problem, that there's no cartridges have been fitted for whatever reason, major failure, really, but that has happened on a few occasions. When we put a camera system downstream of this, we can validate the performance of these filters over time. Sometimes these filters by some operators are pulled out, clean, pressure washed and put back in. That's really not going to work. You really need to replace them. And the major one is, has the filter cartridge sealed properly? So as these filters are slid in, there's a seal at this far end here, which is critical. we find that when there's a leaky filter, then more often not, it's caused by that seal. The other thing that happens is that there's been some work done to see what the efficiency drop is over a number of pressure cycles. So if we drop the pressure on this suddenly and then repressurize it, we're stressing these filter cartridges with differential pressure across them, and that has the effect of making them less efficient over time. And sometimes if the wrong size cartridge has been ordered, it has been known that if they're an inch too long, we just chop off the inch and we'll fit it in anyway. That's not going to fly either. Very often we see an increased mist before there's an increase in differential pressure. So really, it's a question of when does that filter cartridge need changing out. Obviously, it's more to do with the performance of the cartridge. Yeah, I don't know why that's in there again. So how dry do we really need to be? Well, that really depends on what's downstream. So all downstream equipment, there's safety, compliance, and financial impact. So on all three of these, there's regulators, valves, liquid hold-up, that's shown you that pipeline rupture there. Compressors are the key thing, and most compressor manufacturers' specifications are that there should be zero liquid carryover going into the compressor. And then from the gas turbine power station point of view, if there are certainly the glycols and the compressor oil, that can cause blade damage and or blocked fuel nozzles as well. There's been a few instances of that. This is the kit we have. We do either temporary or permanent installations, and normally we're sitting at the 12 o'clock position on the pipeline here. And this is an example of a flange connection here. There's normally an isolation valve between the pipeline itself and the camera. The camera and illumination system sits up here, and it looks through that valve into the pipeline below, so that we can see any liquid that might be on the pipe floor, streaming on the pipe floor, any mist flow that might be between the camera and the pipe floor as well. There is a secondary containment system in here, so to make sure we're safe, even under fault conditions. There's no loss of containment, and we can live stream to the control room, which is really helpful, certainly at startup and shutdown times where the operators do not have steady state. And usually it's at startup where we see significant liquid carryover on occasions. We use image processing for analysing the images, but we also use machine learning later on in the system as well. So the window here is heated. It usually sits about 5 degrees above ambient temperature, which means even if there is condensing conditions in the pipeline, we don't see condensation on the window. And also it's recessed. This vertical section here is a cushion. There's static gas here, and the longer this section here, the less likely it is that contamination will sit on the window. If it does, it's not a problem. It's close the valve, take it off, clean it, put it back in, and you might need to do that once every 6 months, once every 12 months, something like that. And then there's remote access, so that we analyze the system online, and remote users can get in and see the analysis and the videos as well. So we have two systems. One is a flange system for basically anywhere outside the US and Canada. Within US and Canada, they tend to use the thread-elect connection rather than the flange. So there's a threaded version out here as well. Usually there's up to 100 meters or 300 feet worth of cable. This is power over Ethernet, so it's only a single cable going out to the camera. And this system sits in a safe area. It logs the data, and let's say there's a secure uplink to the portal as well. These are a couple of installations. On the left one, you'll see this bracing. It's basically a small bore connection to a large diameter pipeline. So normally there's bracing in place to make sure that this vibrates at the same frequency as the pipeline itself. It's braced against the pipeline rather than anything else to make sure that this vibrates all at the same rate and amplitude. So these videos I'm going to show you are all real-world videos. Data can be used to solve liquid carryover and optimize gas separation systems and filter changeouts as well. When we see liquid carryover, there's normally a bit of a, oh my goodness, didn't know that was there. But there is really adequate technology on the market and improved practices to resolve these problems, really. And I have to say, liquids have been present in 100% of installations to date. So this is an example of compressor oil. So the gas itself is pretty clean. We've got a very clear view of the pipe floor. We can see a scratch here, and this looks like a weld splatter or something in here. This is real time. So the gas is actually moving from the left to the right at about 30 miles an hour. And you can see it's pulling. The only reason this is moving is it's pulling that compressor oil with it. The shape of the compressor oil is quite surprising. It looks like a caterpillar or something. And this is because the ambient temperature is around about 4 or 5 degrees C, and at that temperature, compressor oil is quite viscous, quite dense. At higher temperatures, it spreads out a little bit more than this. But this has just climbed 2 meters vertically. And so it will just continue going. It's moving slowly, but it just keeps on going. And down the left-hand side, you can see our housekeeping data there. So this is the same footage, but in time lapse. So that's that stream coming in. It tries to climb the pipe wall and falls back down and collapses. And then we see a little bit more compressor oil coming in the afternoon, and then drips and drops of liquid coming in over the space of the morning. More compressor oil here. And then now we're beginning to see this mist flow coming in here. These dark shadows coming in represents that mist flow. And then suddenly they stop gas flow. This is a gas terminal, it nothing to do with us, but they stopped gas flow for an hour or two. And then when they restarted, we could see this distributed flow here at the bottom. And then this mist flow got increasingly bad towards the end of the day. That's running towards midnight now. And you can see that that's really quite bad. So now we've run back down round to the middle, to the start again. So this is an example really of what an NGL flow looks like. This is, again, there's no mist flow. It's very clear gas. And we can see these lines running along the pipe floor here. Each of these lines is a liquid line of natural gas liquids. And that's a typical sort of example really of what we see quite often. So we see a lot of mist flow, and this test really is an example of what we're seeing in mist flow. Just to give you an example, on the left here, this is a test rig that will shortly show you some video of mist. Here we go, and that's what we would see on the camera. And the mist flow will come and go. It's clearing again now, and then it'll come back again. And so we can see that trend of mist increasing, decreasing throughout the day. And when we put a score on that, we trend the mist flow. So this is an example of a process failure. So we've got solid material on the pipe floor here, sudden onset of mist flow. And it stayed like that for quite some time. It turned out that this was a process failure. It was at a gas terminal, and on the supply side, a hole had appeared in a heat exchanger and allowed glycol straight into the gas flow. About 15,000 gallons of glycol were dumped into the gas line, costing over $1 million to remove by pigging and disposal. So quite an expensive event, really. This is another example really here where we see a liquid event here, a little bit of liquid here, and then all of a sudden See a lot of liquid coming over the full field of view, a pretty large liquid event. And this is in real time. So a lot of liquid going down the line. What we were able to do in this instance is basically look at the water dew point in blue here and the hydrocarbon dew point in tan color. The orange line here is that this start here of that event here. And you can see neither water dew point or hydrocarbon dew point reacted. In fact, the hydrocarbon dew point decreased a little bit, which is quite important. But neither went into alarm. And this is how these liquids are getting into the systems without anybody knowing, without the camera present. The operators were thinking that everything's normal, everything's continuing as it should do. But in reality, they had a major problem. So this is what the pipeline looked at when they stopped that gas flow. And we can see the liquids and particles on the top of the liquids. They turned out to be unsulfide and a little bit of norm as well, not naturally occurring radioactive material. So we could see that liquid and measure it and tell them how much was there. And then this is what happened. This is time lapse when they depressurized the line. So from the graphs, you might think, well, it's not NGLs. It must be glycol. But you can see now those liquids are evaporating. And if they're evaporating, they can't be glycol and they can't be compressor oil. The only thing it can be really is NGLs. And then this is what we're left with after the flood. So this was in a flow metering station. So this solid material here is now going to give a permanent offset on the flow meters until they're cleaned out. So having cameras in flow metering stations for flow assurance means that the operators know when that meter tube needs to be cleaned, either because of solid material in here, or sometimes over a period of time, we go from what is a very clear view of what the pipeline is to quite a dark and black sort of return as well. And that's a trigger point for operators then to clean the meter lines. So why is hydrocarbon dew point important? Well, it's the dew point, it's the determining factor of whether the gas is wet or dry. It's specified in a lot of tariffs and a lot of contracts that the gas shall be no wetter than a certain dew point. So contractually, it's quite important, but also from a safety point of view, it's very important as well. I was going to say, why do we care? Well, safety, really. We're giving away energy if the gas has got liquids in, but fiscal measurement and compressor failures, those really are the main things. Asset integrity comes into it as well, in terms of the pipeline integrity as well. But we've found that there are some fundamental problems on how dew point is obtained and used. So let me expand on that. So to the left, we're going to have a video where the process temperature is +7 and the hydrocarbon dew point is -40. So we would need to cool that gas by 47 degrees C before we started seeing condensate. And I'm going to take the pointer off to start the video on this, sorry. So that's what we see. This is a pretty dry gas. It's moving around a little bit. That's fine. That's because it's at pressure and it's basically heat haze kicks in at higher pressure more than it does at atmospheric pressure. So that's quite normal. That's dry gas here. On the right-hand side, we're going to have a video for a process temperature of +26 and a hydrocarbon dew point of -47. So in this case, we'd actually have to cool the gas by 70 degrees before we started seeing NGLs or condensate fall out, really. And this is what we see. This is a typical example of NGLs. We can see those straight lines forming. We were just downstream of a bend, so it's quite chaotic. There's quite a lot of churn going on in those liquids on the pipe floor. But certainly, when you compare a dry gas on the left to what we're seeing on the right, there's a considerable difference. This was at a custody transfer point, and so that was able to be corrected once we illustrated what was going on. So this is an enormous error. It's 70 degrees, and we're seeing liquids there. It's not like a pressure sensor that's slightly out of calibration. There's some fundamental errors going on. So equation of state, we'll go through that in dew point charts, assumes equilibrium between the gas phase and the liquid phase. Sampling systems are designed to remove liquids and prevent damage to gas analyzers. And then if we're calculating hydrocarbon dew point rather than measuring it, there's some added uncertainty into there. So with this minus 47, then what's happening is the gas is moving much quicker than the liquids, as we've seen before. That gas is dragging that liquid along with it. So the gas is much faster than the liquid. So the interesting thing for us when we're doing the research on the data we've got, and incidentally, we can't do this in a flow loop. We can only see this in real world conditions. Then what happens when that gas flow stops? So as the gas flow is slowing down, those liquids sort of begin to pool at the low point of the pipeline. And if I skipped a little bit here, there we go, then that forms a continuous sort of stream at the bottom, or just a pool of liquid at the bottom of the pipeline. But the interesting thing really is what happened to the hydrocarbon dew point. It was minus 44.7. It increased to minus 30.3. So that's what drew our attention. We said, we know in this instance, we've got liquids present. Why would, if it was a dry gas, why would stopping the gas change the hydrocarbon dew point? So then we started looking at BTU, and this is a trace of the BTU. The orange is the flow rate here. Let me just get that laser back. The orange is the flow rate here, and you can see that period here. I've just shown you where the flow stopped. And when that happened, the BTU started jumping around, and it spiked here when the flow stopped. So we wanted to look at that a little bit deeper and said, well, why is the BTU jumping? And so we looked at incidentally, the cost of that, just that 12 BTU jump is about $3 million or $1.3 million a year in lost revenue. And that's not all the liquids that are in the pipeline that aren't being counted. So we looked at C6, the C6 plus content from the gas chromatograph, and really that's what's driving that BTU increase. That's what's driving the hydrocarbon dew point increase as well. So what's happening is when the gas flow has stopped, the gas space above that liquid is now stationary, and as those liquids evaporate and change from liquid phase to gas phase, that's now when the gas chromatograph can pick it up and starts looking at that as well. With this big difference in flow between the liquid and the gas phase, then that dry gas is masking the presence of the liquid underneath it. In fact, when we looked at the C6 plus change, so what happened in percentage terms between what the C6 plus was doing in this phase with the gas flow running compared to here, what sort of change was that? And actually that was an 84% change in C6 plus, simply because the gas stopped. And we think this is a major factor in why we're seeing this concern about hydrocarbon dew point. Interestingly, when we looked at the other gases, or hexane, pentane, well, C65432, they all increased quite logically, but they all increased when that gas flow stopped. Methane obviously dropped because the others increased. So what we're saying is, from observations at multi-locations, it's clear that there's a big difference between lab conditions and online analysis. So if you were able to take a gas sample that was representative of what's in the pipeline, and if anybody's had any dealings with wet gas flows, you know how difficult that is. But let's say that we've taken a sample and it's representative of what's in the pipeline. That sample would have some liquid in it and it would have some gas in it. That liquid would come into equilibrium with the gas phase, and we send it to the lab, and the equation of state works out, and hydrocarbon dew point works out, and everything works. However, in a pipeline, we've got the gas flow running at, let's say, 12 meters per second, and the liquid is running at less than half a meter per second underneath it. Then in that state, the liquid is vaporizing into a much, much bigger gas volume than on the left. And so that it's more difficult to pick out whether there's liquids there. In fact, almost impossible. So this is actually a steady state. It's not a temporary thing. We've seen this exist for weeks and months on end, where the hydrocarbon dew point is reported as dry gas. And when the transmission company goes to the supplier and say, you're sending us a lot of liquids, the supplier can say, no, it's not us. Look, we've got dry gas, it's -40. It's not until they're able to show them the videos and say, look, this is what you're sending us, that they realize what's going on. And it's new information for both sides of the fence line as well. The other system that will cause a problem is the standards. Everybody's at the moment doing everything according to the standards. Everything is correct, but we've still got this big error. So API 14.1 is the standard that everybody uses for gas analysis, certainly the gas sample systems. It governs and guides how that sample is taken and handled between taking it from the gas pipeline to the analyzer. So obviously the gas analyzers normally work at atmospheric pressure. That drop in pressure causes a drop in temperature. So they all need to be heated, more and more heat between here and the analyzer. But there are also membrane and coalescing filters between the sample point here in the middle of the pipeline and the analyzer. So it's in the middle of the pipeline, according to the standard, simply to avoid any liquids that might be on the pipe floor. So it's intentionally missing those liquids. And the reason for that is the last thing you want to do with a gas analyzer is put liquids through it. It won't last very long if you do. And you'll be constantly changing the gas columns in the GCs and maybe even writing some of the analyzers off. So as I said before, it's the glycol and compressor oil that isn't monitored by gas analysis, and liquid phase hydrocarbons are not monitored either. When lines are pigged, usually it's the glycol and compressor oil that is taken out a lot of the time. The liquid phase hydrocarbons are more are lighter and will evaporate easily. So by the time the pressures drop, they've usually gone. So looking into API 14.1, it does have a let out. It says sampling of multi-phase flow is outside the scope of this standard. But it also says hydrocarbons can contribute significantly to the energy content, the BTU, of the gas, and their presence in the line should not be overlooked. But that's exactly what we're doing at the moment with the standards the way they are. So sample systems are specifically designed to avoid and remove liquids. And when present, it leads to significant errors in BTU. And you won't know. You won't know unless you can see what the liquids, if there are any liquids there or not. So very often our systems go in to validate the GC and other gas analyzers. So one point to note is low point drains. Quite often there's a standard practice. If liquids are suspected, go open a low point drain and see if any liquid comes out, which is quite a logical thing to do. But if you have an example here of this, of just this pipeline, horizontal pipeline, and we have a tapping point below, if we filled that section with liquid and then started up a gas at 30 miles an hour, well, we've just created a carburetor. And so this area here is low pressure. So you aren't necessarily going to get liquids out of this system. They'll just go straight, as soon as you start up that gas flow, they'll just go straight into the gas flow. So the poor old operator, the engineer, has got a hydrocarbon dew point saying, I've got dry gas. I've just opened my low point drain. There's nothing coming out. That's definitely dry gas. And then we put a camera on and say, well, not so much. We need to look at this and see what we can do to improve the situation. So hydrocarbon dew point calculation is another level, if you like. It adds that complexity. So if we calculate hydrocarbon dew point from GC data, so this is typical gas here, it meets all the normal specifications. And the question is, does it meet the hydrocarbon specification of -7 degrees C? And the answer is, it really depends on the C6 characterization. So in quite a few gas chromatographs, the C6, everything heavier than C6 is all lumped into one number, which is fine. If you're calculating BTU, that's fine, because this is such a small number, it's not going to really have much effect on BTU. But if you're trying to establish what the hydrocarbon dew point is by lumping all the heavy ends into one number and then effectively guessing what that characterization, the split of the C7, 8, 9, 10 will be, then you can run into major problems. So probably all familiar with the hydrocarbon phase envelope. We're in operations, we're always trying to keep to the right of this. This is gas phase only here. This is water dew point in the blue, and hydrocarbons in the purple. So we're always trying to keep to the right of that curve. That curve will move left and right depending on the characterization of the gas. And there are 6 normally accepted methods of treating what that single number for C6 plus is. So we're going to split it, we're going to ignore it, is the first one, and just say it's C6. Or we're going to split it 60-30-10 or 47-35-17, a number of different methods to do that. The best one is the bottom one, where we're looking at measuring it up to C9 and then expanding from that. But as you might expect, if you've got 6 methods, you get 6 different answers, ranging from, for that gas specification, ranging from minus 69 to 51, 48, 5, 14, and plus 34. So when we look at the phase envelope difference, it's just so wide. The Cricondotherm span between all of these is 104 degrees C. So it really does impact on the conclusions you can draw about whether the gas is dry or wet. If you go a little bit further and say, okay, let's assume now we're going to model now a wet gas. So 12 ppm of that C6 plus element has now changed phase and it's now liquid. So what does that do to the dew point? And as you can see, from all cases, it makes the dew point drier. So as you would expect, it's the same fluid. It's just that some of it is now liquid phase, so the gas phase has got to be drier. However, if all you've got in the analyzer is one of those numbers, you say the gas is dry. So I'm going to skip that for a minute. This one is an example of what we did on 2 trains on a system, and the gas comes in at the bottom here, splits here into train 1 on the left and train 2 on the right. And it goes through a knockout drum before compression and then up to the compressor here. So these cameras were installed at this position here, just a meter or 2 away from the compressor inlet. So we're between the knockout drum and the compressor inlet. And the reason for this study was they wanted to understand the difference they were getting between the performance of train 1 and the performance of train 2. And when we looked at the 2 trains, we saw very, very different images. This is train 1 on the left, which was very, very dark, and train 2 on the right. Now, during the study, we were able to take a lot of process data and combine it with the metadata from the image and create a machine learning model that showed them that actually one of the driving factors was differential pressure between the 2. When you can see this little loop here that isn't present here, that was sufficient to cause a small differential pressure, which caused preferential flow of liquids down one side than the other. That was one of the major findings. The other one I'll go into in a minute. But this is some of the scariest videos we've shown so far. This is time lapse of a plant trip. It happened on this site around about midday. You can see the mist flow coming and going, and eventually around about midday you'll see a sudden flash as the gas depressurizes, and then all of a sudden you'll see, as the mist clears, you'll see, there we go, a sudden flash, and then we can see liquids appearing on the pipe floor. So that sudden depressurization and sudden drop in temperature has caused those liquids to drop out in the pipe floor. And remember, now we're between the knockout drum and the compressor. So these liquids, when at startup, are going to go straight into the compressor. So we got some real-time footage of that. This is what that looks like at startup. So just beginning to roll now, a little bit of movement, and then all of a sudden a rush of liquids. So bear in mind, we are about a meter away from the compressor inlet. They got away with it this time. There was no failure, but you can see as that liquid decays away, all the muck and rubbish that is on the inside of the pipeline. This is an unpiggable section of line, and sudden increases in flow rate would actually dislodge some of that as well, and that would go into the compressor as well. So safety note, really, if you guys are on site and you know a compressor is starting up, particularly after a trip, or starting up at any time at all, then get to the control room, get to a safe area behind a blast wall, because seeing some of these videos, knowing what's actually going on, they were just repeating it through again, gives you a better awareness of the risks involved, and particularly at startup. So as I said, we use metadata, we use the image data, the brightness variance to create a machine learning model, and we gather as much of the process data as we can. And this is just 3, but we actually use 15 parameters on the input. So pressure, level, flow, or pressure, flow rate, and temperature. And that's the inputs to the machine learning model, and the brightness in this instance is the output. So it's a random forest model, and we train it to the best fit we can on 80% of the data, and then we test it on the remaining 20%. And you can see a pretty good fit. So we get, if you like, a digital twin of what that separator is going to do under different operating conditions of pressure, temperature, and flow. But the most important thing is that we can build this feature important graph of which of those process parameters is driving the liquid carryover. The interesting thing was temperature 3 was just one of the 2 feeds was the main driver on this one. The differential pressure, as I said, is the second one, and interestingly, liquid level in the separator. So we were finding that it's a really easy win, really. The level control needed to be improved, because every time the liquid level got too high, we saw more mist flow, more liquid entrainment as the liquid level got higher, and then valves opened, it drops, and it goes away again. So what we're saying basically is, this is the standard suite of analysis systems with a sample probe for gas analyzers for a GC, maybe a hydrocarbon dew point, moisture, and H2S analyzer. This is standard stuff at a custody transfer suite. Pressure and temperature as well. If we put a camera system alongside that gives a much better and more complete picture, if you like. So just to conclude, hydrocarbon dew point has been a trusted standard in the industry, but it does rely on single phase equilibrium. Unfortunately, if we're relying on that to tell us whether it's dual phase, we're going to come a cropper. We're not going to get the right answer, really. So recent studies and research have shown that equilibrium does not exist in gas flow, and it causes significant errors. The use of process camera provides a more reliable reporting of liquid carryover. So from a key takeaway point of view, certainly separator systems can be improved once the problems are understood. And that's what we're all about, really, is understanding, getting a handle on what is happening with the separator system under different flowing conditions. Hydrocarbon dew point is not an indication that the gas is dry necessarily, or the fluid is dry, should we say. An unknown liquid carryover is common. And it has a large safety and financial implication as well for both the supplier side and the receiver side of gas. So underreporting by just 12 BTU is a £1.3 million revenue loss for the supplier, and real-time visual monitoring is essential to manage liquid carryover risk. That's pretty much it. I think I've just about come to come. It's 10 past, so just about run for
Yes,
time. So
you got approximately 61 minutes. I'm counting them by the minute, but that was right on time. So thank you so much, Paul, for that. I think we have Dr. Mark waiting for us to start his next segment, but I think we might take 3 more minutes just to answer a few questions that I got from people here. The first question is asking, hi, Paul, you mentioned poor amine quality. What is your definition of poor?
yeah, good question, really. That is better answered by probably somebody like amine experts. There is an increasing amount of liquid going into the amine system. I've seen various percentages, sometimes 10, 20% of that amine is actually hydrocarbon liquid. There's very often there's scavenger systems to remove that from the amine and filtration systems to remove it as well. But once it gets into the system, it's quite expensive to get out really. But generally, yeah, I would say about 10, 20%. There was a report that the amine system does need some level of liquid hydrocarbon in order to function. That's not right. That's been debunked. So the lower the hydrocarbon liquids in the amine system, the better.
Okay. Next question. What's your take on the application of Coalescer? How efficient is it compared to separator that you presented earlier?
Yeah, I mean, there are different styles of coalescing. So the coalescer, by coalescer, I think you mean a depth filter or a cartridge filter. Generally, they are far more efficient. Certainly in lower microns, that generally is the case. So I gave the example of NGL carryover following NGL recovery. So that really is a case where when that gas is cooled by Joule-Thomson, that is the perfect scenario to form a very fine submicron mist flow. And you go to the filtration guys and separation guys and ask them, what's the most difficult thing to filter out? And it's that very low submicron filter or submicron level of mist, really. So I did put up some numbers on the separator. It does depend on vendor, but some of them are claiming down to 10 microns on a separator system, and then on the coalescing filter or the depth filters, depends on the manufacturer. Again, some will claim down to one micron. Some will claim specialists actually will claim lower than 1 ppm. There is one specialist manufacturer that has a completely different seal mechanism because they specialize in this very low micron size mist. So it depends, on the vendor itself, really, on the specification of what's there. But generally, knockout pots will get rid of the heavier ends, or the higher micron size, and the coalescing type filters will get rid of the mist flow, the fine mist flow.
All right. The next question is related to the mist flow, and I hope we can answer this in under 1 minute. So the question is, what causes the mist flow?
That's a really good question. The times we see a mist flow is downstream of either decompression or compression. So, and we didn't realize on one of them, generally when we see a mist flow, it is fairly stable. You might not like it, but it is fairly stable. It'll get worse at night when the temperature drops, and it'll get better during the day when the temperature increases. It might even clear completely certainly in springtime in the States. What we're seeing is some of these mist flows are actually clearing completely during the day, and then they come back again at night when the temperature drops. It's not a dew point meter, but that is a fundamental observation of dew point, if you like.
All right.
So yeah, it's decompression really is the big one via Joule-Thomson. What we were seeing on one compressor entry at that compressor entry sign was the mist flow was going up and down very, very rapidly on occasions. and that coincided with the recirculation side of the compressor. So when flow rate is low, they recirculate the gas. And of course, you're compressing the gas, creating this misflow, and then taking it and putting it around to the front end of the compressor. If that's not dealt with properly, then you're going to cause problems in dry gas seals.
All right, sounds good. I think that will be it for the questions for this segment, because we have Dr. Mark waiting to jump in for the next segment. If anyone has any questions related to the Process Vision products, these very interesting cameras, I just dropped the link to contact the company anytime. Feel free to reach out to them. You also have Paul's probably email showing up in front of you. You can reach out to him as well. Thank you, Paul, for this amazing segment. That was really interesting, and hopefully we can see you again in other events as well.